Hi, welcome to module 26 of week 5. So, in this module we will take off at where we left in week 4. So, we started talking about sequential elements, and in this module what we will do is we will look at basic sequential circuits, fairly simple circuits, but many of these are building blocks for other circuits, and we looked at D flip flops, T flip flops and latches and so on. So, I want to construct a few circuits using flip flops before we move on to slightly more advanced topics. So, let us start with a very simple thing. So, something called a frequency divider. So, let us take a look at the circuit here. We have a T flip flop, and if you think about what would happen if I permanently connect the T input at 1 for this flip flop. So, I have a clock signal that is coming in, and I am permanently tying the T input to 1. If this were to happen, then I want you to think about what would happen to Q naught. So, let us say I give you a clock signal. So, the clock signal is a periodic signal, and it is a T flip flop which is triggered on the positive edge, which means every time the clock goes from 0 to 1, the output Q naught is supposed to toggle, right. So, what would happen is if I have let us say Q naught at 0 initially, this clock pulse would toggle it to 1, the next clock pulse will toggle it to 0, the third clock pulse will toggle it back to 1, the fourth clock pulse will toggle it back to 0 and so on, and this would be the waveform that you would get. The interesting thing about this waveform is that if you look at this waveform and this waveform, you can see that the logical value 1 is kept for one full cycle, and logical 0 value is the output for one full cycle, and then again 1 and again 0 and so on. So, if you have this signal of clock frequency f or equivalently time period 1 by f, what you are getting here is you are getting a clock frequency of f by 2 or equivalently time period 2 by f, and therefore, we can say that Q naught is a signal that is actually dividing the input clock frequency divided by 2. So, Q naught is a signal which is the clock signal, you take the frequency of it and divide by 2, that is this clock signal, right. So, this is fairly interesting, but a very simple circuit, and something else that you can do with it is you can take this output and connect it as input to another T flip flop. What do you think will happen now? So, you have Q naught which is flipping at f by 2 frequency. So, it is switching at frequency f by 2, and if you connect to this one, then you can treat this as the clock signal, Q naught as a clock signal and Q1 as the data signal, and in that case what would happen is if Q1 was at 1, then when Q naught goes from 0 to 1 it will toggle, and when it again goes from 0 to 1 it will toggle back, it goes from 0 to 1 it toggles up and so on. Now, you can see that the relationship between Q1 and Q naught is that Q1 runs at half the frequency of Q naught, in turn Q1 runs at 1/4 the frequency of clock, and this is a fairly interesting thing, right. Very simple digital circuit can give you something which is very powerful. You get a frequency divider very nicely. So, this is something that can be used in your digital circuits. So, if you want to run different parts of the circuits at different frequencies, it is possible to actually derive these clocks which are at, the rate of these clocks. So, you can take Q naught and give it to another design which has to run at half the frequency, or you can take Q1 and give it to a design which has to run at 1/4 the frequency and so on. And with this kind of a setup, you can actually design circuits which can run at f by 2 power n frequency. So, you can do any division of, so the frequency f itself does not matter. What you will get from Q naught and Q1 is half the frequency, 1/4 the frequency and so on. You attach more and more flip flops like this, you will get 1/8, 1/16 and what not. So, it is a fairly simple circuit, but a very interesting circuit. Then there are lots of places where you want to count. For example, I want to count the number of electrons that pass through, right. If I want to do something like that, I need a counter, and there are two kinds of counters, up counter and a down counter. Up counter counts 0, 0, 0, 0, 0, 1 and so on, and down counter would count down. So this is a circuit which actually does what is called a 3-bit up counter. It's called a 3-bit counter because you have 3 flip flops, Q0, Q1 and Q2, and there is a certain connection, there is some method to this madness here, the connection here, and let us see what happens to each of these signals Q0, Q1 and Q2. So let us start with the first waveform Q0. So Q0, if you look at it, it's there is one permanently connected to its toggle input and the Q is tapped out, right. So you are seeing Q being tapped out. So you will see that Q0, like I mentioned in the previous slide, is switching at half the frequency of clock. So you will see that when clock goes from 0 to 1, Q0 went from 0 to 1, and again it went from 0 to 1 here. So Q0 toggles from 1 to 0 and whatnot, and that will continue for the rest of the time because you have permanently tied the input at 1. So one thing to notice here is that we talked about the notion of delay, right. So there is going to be a slight delay between the clock's arrival and the Q being ready. So I talked about in the previous module, I talked about clock to Q delay for flip flops. So as soon as the clock comes, Q is not going to be instantaneously available. So it is going to be available after some period of time, and this delay I am going to call it, this is the clock to Q delay of this T flip flop. So this is the waveform for Q0. Now let us go and look at what Q1 has. So the flip flop Q1 is also a toggle flip flop. It takes 1 as its input, which means it is supposed to toggle for every clock cycle, but the clock that is being fed to this flip flop Q1 is not the input clock, but it is coming from Q bar, or here in this case Q0 bar, right. Q0 is this signal, so this Q bar connected here would be Q0 bar. So you go and look at Q0 bar. So this is Q0, and again this flip flop Q1 flip flop is actually a positive edge triggered flip flop, but you are feeding Q bar to it or Q0 bar to it. So you go and look at Q0 bar, and whenever Q0 goes from 1 to 0, that is equivalent to Q0 bar going from 0 to 1, which is what you are feeding to Q1. So whenever this goes from 1 to 0, this flip flop is triggered and it will toggle its value. So assuming that Q1 starts at 0, then this edge, this negative edge of Q0 will be a positive edge for Q0 bar, which will trigger Q1. So Q1 will go and toggle to 1, and then it toggles back to 0, it toggles to 1 and so on. Now if you go and look at what time Q1 is toggling, it has to, so clock toggles Q0, Q0 in turn toggles Q1, right. So there is a definite time period between the flip flop Q1's clock input and its output, right. It is the clock to Q delay of this flip flop, right. So if you go and look at the relationship between the clock signal, this red waveform here and the green waveform here, then you have one clock to Q delay that goes and changes Q0 or equivalently Q0 bar. Let us assume that both Q0 and Q0 bar are available at the same time. Then you take that and you are connecting it to Q1, so that will be another clock to Q delay times away. So this is one clock to Q unit and this is another clock to Q. So you have two clock to Q delays to toggle Q1, and Q1 is toggling as shown in the green waveform. Now if you go and look at Q2, again it is toggling for its every clock cycle, but the clock is derived from Q1 bar. You go and look at the negative edge of clock Q1 and see at these points Q2 should toggle. So Q2 is toggling, and this will be again another clock to Q delay from Q1's toggle itself. So overall there are 3 clock to Q delays, or 3 times the time for clock to Q delay. If clock to Q delay is, let us say 0.1 nanoseconds, then from the moment this is triggered, it will take 0.3 nanoseconds for Q2 to flip. Now if you go and read the entries Q2, Q1 and Q0, you can see that Q2, Q1, Q0 is 0, 0, 0 or count 0, 0, 0, 1 or count 1, 0, 1, 0 or count 2 and so on. It goes up to 1, 1, 1. So Q2 is 1, Q1 is 1, Q0 is 1. So from bottom to top it is 1, 1, 1, that is 7. But something interesting is happening after that. You have each of them at 1 and each of them is going to toggle the next time around, because this clock, this red waveform, that clock is coming in, the blue waveform will toggle. Because the blue waveform is going from 1 to 0, so Q0 is going from 1 to 0, which means Q1 will toggle, and Q1 is going from 1 to 0, so Q1 bar is going from 0 to 1, so Q2 will also toggle. So what you are seeing is, you are seeing 0, 0, 0 here, right. So we counted 0, 1, 2, 3, 4, 5, 6, 7, in every clock cycle we have one unit and it goes to 0. And the interesting thing here is, the moment you get 0, the behavior is going to be similar to as though we are starting from 0 here. The only thing is, we have this clock to Q delay that got added up and that was not here in this part. So this will keep cycling as 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7 and so on, and this is called a up counter. So the reason why it is not counting to infinity is that we have only 3 flip flops. So this is just like the speedometer that I have been talking about for a long time, right. So if you have a speedometer that has only 3 digits, right, it will go from 0, 0, 0, it will go all the way up to 999 and it will go back to 0, 0, 0, right. You have no way to say that it is 1000 once it rolls over. So the same thing is happening here, it is rolling from 0, 0, 0 to 1, 1, 1 and it rolls back to 0. So this is called a up counter. Equivalently, we have something called a down counter. A 3-bit down counter is very minor change. You take the same 3 flip flops and connect them, connect all the toggles to 1. This time, instead of connecting Q bar to the clock input, connect Q to the clock input. So we are connecting this Q0 as the clock for Q1, Q1 as the clock for Q2 and so on, and you tap out Q0, Q1, Q2. Again, if you go and look at what would happen, you would see that clock is running at whatever frequency it is, Q0 will toggle every time the clock pulse comes in. So you have Q0 which is toggling every time the clock pulse comes in. So in this clock pulse, this one is toggling to 1 and this clock pulse it's toggling back to 0 and so on. And since we have connected Q0 as an input to Q1 as its clock, right. So this flip flop Q1 has Q0 as its clock, then Q1 toggles from 0 to 1 whenever Q0 goes from 0 to 1. Similarly, when Q1 goes from 0 to 1, Q2 also goes from 0 to 1, except that there is a small delay, right. So from going from clock to Q0 is a one clock to Q delay, again another clock to Q delay and another clock to Q delay. So this will take 3 clock to Q delay units, and this is the basic setup. Now if you go and read what is going to happen, again Q2, Q1, Q0, right, 7, so this 111 is 7, then you have 110 which is 6, then you have 101 which is 5, so it goes all the way down to 0, right, all the way down to 1, so you have 0, 0, 1 and then it goes back to 0, and here we started with 0, right. So you can imagine that if this is running forever, then this 0 will then toggle to 7 and so on. So if you go and read the values of Q2, Q1, Q0, it is going in the descending order, right, and this descending order is essentially the down counter, right, you are counting down. And as before, when you count from, let us say it is a 3-bit value, it counts from 7 down to 0 and it goes back to 7. So there is, it is actually an increment going from 0 to 7, but then because we do not have enough bits, that is what can happen. So you will count from 7, 6, 5, 4, 3 up to 0 and back to 7. If you give one more bit here, then you will start with 1111 which is 15, you will go from 15 down to 0 and then you will go back to 15. So you can add as many flip flops as you want to the right side, and you should read the number from right side to left side, that will give you the down counter, right. So we have discussed two counters, up counter and a down counter, but there is a small issue with both these counters. The counters are what are called asynchronous. The flip flops are not all synchronized to the same clock. So imagine I have a big enough width of a counter. So I have a 100 bit counter, which means it can count from 2 power, so it can count from 0 to 2 power 100 minus 1. Let us say something like that. A big enough counter can encounter a problem, because flip flop 0's output is going to delay flip flop 1, because flip flop 1 can toggle only when flip flop 0 goes the output of flip flop 0 is ready, right. So there is a clock to queue delay from the input clock to flip flop 0. There is a delay because of flip flop 1, its effect is seen in flip flop 2, the effect of flip flop 2 is seen on flip flop 3 and so on. So if I have 100 flip flops which are in a chain, you will see that 100 times the clock to queue delay, let us say it is 0.1 nanoseconds, so 100 times 0.1 would be 10 nanoseconds. So you will see that the 100th flip flop is actually flipping 10 nanoseconds after the clock pulse comes in, and if your clock width is greater than 10 nanoseconds, you are still getting all of that done in one clock cycle. But what could happen is, if your clock width is, let us say, less than 100 nanoseconds, let us say it is 75 nanoseconds, right, then what would happen is your counter is actually counting at a rate which is beyond the clock width. You have, so going from one count to the other, in the next clock pulse you would want all the bits in the counter to settle down to a value, right. You would want, if it starts from 0, you would want 1, but this will not happen. What will happen is, in one clock cycle, some of the flip flops will settle down to the count values, but some would not have, and this is a problem. So for an external observer who is going to take the values for every 75 nanoseconds, they may not read the correct values out. So what we need is, we want all the flip flops to work based on the clock. So the clock should be the triggering signal, and based on the clock that comes in, all the flip flops should settle down to their respective values within one clock cycle, and such a circuit would be called a synchronous circuit. What we want is each of these flip flops to change in such a way that their output values go down to their final values within one clock cycle. So let us look at the 3 bits. So let us go and design a synchronous circuit. Let us see how to do that. So what we want is, we want in clock cycle 0, 1, 2, 3, 4, 5, 6, 7, 8 and so on, we want to go from 0, 0, 0 to 0, 0, 1 to 0, 1, 0 to 0, 1, 1 and so on, all the way up to 1, 1, 1, and again go back to 0, 0, 0. This is what we want. If you go and look at what is happening at Q naught, right, Q naught is toggling every clock cycle, that is fine. Now you go and observe Q1, so Q1 is changing here, here, here and here, Q2 is changing here and here, right. These are the changes that you see in Q0, Q1 and Q2. This is not something that is new to you. Now let us see how to derive some synchronous circuit. Synchronous circuit should mean that you should take a single clock pulse, and your inputs should be in such a way that the output can be settled in just one clock cycle. So let us look at this. So Q0 is toggling every clock cycle, so this is fairly easy, we saw this earlier, and if you have just one bit, right, then there is nothing, so it is anyway taking the clock input, so it is actually synchronous with respect to the clock. If you go and look at Q1, Q1 is toggling every time Q0 changes from 1 to 0. So you go and look at this, Q0 is changing from 1 to 0, so Q1 toggles, Q0 is going from 1 to 0, Q1 toggles, again 1 to 0, Q1 toggles, this is again going from 1 to 0, Q1 toggles, right. So Q1 toggles every time Q0 changes from 1 to 0. You go and look at when Q2 is toggling, so Q2 is toggling every time Q0 is, so Q1 is 1 and Q0 changes from 1 to 0. So you see, so let us take this a little slowly, Q2 is at this point it is at 0, right. So and it has toggled to 1 in clock cycle 4, and what are the conditions that is making it toggling? you go and look at clock cycle 3. At the end of clock cycle 3, we have Q1 is 1, and in the subsequent clock cycle Q0 is going to go from 1 to 0. So, whenever Q0 goes from 1 to 0 and Q1 is 1, Q2 is toggling. Let us validate this statement. So, let us go and look at the second place where Q2 toggled, it is toggling here. So, I said the statement I said was whenever Q1 is 1 and Q0 toggles from 1 to 0, Q2 will also toggle. That is the statement here. So, we are seeing that Q1 is at 1, Q0 is toggling from 1 to 0, so Q2 seems to toggle from 1 to 0. So, and you will see that this is going to happen one after the other, right. So, this is an interesting observation. Now, I want you to take a break and think about when will Q3 toggle. So, go and think about it, solve this on a piece of paper before you come back to the video. So, my question is when should Q3 toggle. So, I am going to give you the answer in the next slide, but I want you to take a minute and think about it. So, I have given a circuit here which actually has a 4-bit counter, and you can see that Q0 is toggling every clock cycle, Q1 is toggling whenever Q is toggling from. So, you can see the input, right, it is whenever Q1 is at 1, right, this will toggle, and for Q2 the condition that we derived was Q1 must be 1 and Q0 must be going. So, you look at this, Q1 must be 1, and if Q0 is currently 1, we know that it is going to switch to 0 next clock cycle, right. We do not have to wait for this trigger to go from 1 to 0. If Q1 is 1 and if Q0 is 1, we know that Q0 is going to go to 0 the next clock cycle. So, I do not have to look for the switch from 1 to 0, instead I will go and look for the value which is 1, right. So, that is what is done here. You go and look at Q1 being 1, and if Q0 is 1 here, in the next clock pulse you know that it is going to go to 0. So, which means there is a transition from 1 to 0 on Q0, and however the current value of Q1 is 1 and Q0 is 1, these two conditions is enough to go and toggle Q2. And the answer to my question in the previous slide is that if Q2 is 1 and if Q0, so and if Q0 and Q1 they both go to from 1 to 0, then you will have Q2 toggling. So, Q3 toggling. So, look at Q3's input, Q3 will toggle when Q2 is 1 as well as Q1 is 1 as well as Q0 is 1. If all three are 1, then this will toggle. So, it is actually a fairly simple circuit now. So, the condition is for any nth bit to toggle, then you have to have a logical AND of all the previous bits. If they are all 1, then this bit will flip. So, if you want to get a counter with 5 bits, then you have Q0, Q1, Q2, Q3. For Q4, you take this input and with Q3 give that as toggle input to flip flop Q4, that will be a 5-bit counter. So, these are the waveforms that you are seeing here. So, clock is at whatever clock frequency it is. If you go and look at when Q0 will switch, let us look at the delay between Q0 and its clock. So, Q0 is going to flip a certain time unit away from clock, right. So, that is 1 clock to Q delay. So, you have 1 clock to Q delay. Then if you go and look at when Q1 will toggle, so you have Q0, so Q0 is going from 0 to 1 and Q1 will toggle if the input was already 1, right. So, if this is 1, then if the flip flop Q1 setup time is satisfied, in which in this case it should be because Q1 is here, right, Q1 clock pulse is coming here, it is the same clock that is going. So, you see this now clock, it is the same clock that is going everywhere. So, with respect to this clock, you go and look at its input, the input is Q0, right, has it settled down? Yes, it has settled down, which means Q1 can flip in clock to Q delay away from this clock, not from Q0, right. So, Q0 is data to Q1 and clock is the input clock signal itself. So, the triggering signal is clock, the sampled signal is Q0, the sample signal Q naught remains at 1 when the triggering signal clock is coming in. So, as long as the triggering signal comes in only when the sample signal is stable, then the setup time would get satisfied. So, it has been stable for almost 1 clock period, and for a good flip flop this should be enough. So, this toggles. The same thing happens for toggling down also. So, you go and look at this place where Q1 is toggling from 1 to 0. So, the clock pulse is this, and you go and look at sampling of this waveform, right. So, Q naught is at a stable 1, right, Q naught is a stable 1, and Q1, the previous value of Q1 is 1, right. So, because of which it can go down to 0. So, and this happens from with respect to Q1, Q2 is toggling, and with respect to Q2, Q3 is toggling, but the clock signal that is given is the same clock pulse. So, what you are seeing essentially is the delay is measured away from the clock, and each flip flop has a certain time unit, a clock to Q delay that is required for the output of the flip flop to switch. The inputs, however, are ready when the clock pulse comes in. So, all the inputs are remaining stable. You go and look at this condition, Q1 is 1, Q2 is 1, and Q naught is 1 when this clock pulse comes in. Since all three are stable, the input, this input will be 1. So, it will take AND gate delay, whatever delay of the AND gate it takes and so on. Eventually the AND gate will settle down. We will hope that it is going to get settled down before the clock pulse comes in, and when the clock pulse comes in, all of these are stable, the AND gate will have a stable value as output, which means the toggle input is seeing a stable input. So, then Q3 can toggle because it is sampling, right. So, this one is sampling T. So, when it samples T, the output should toggle in this flip flop. So, it is toggling. So, you can notice that the delays are not adding up. From clock, all the Q bits are only one clock to Q delay away. So, then what is hidden here is, what is not shown in the waveforms here is that there is a delay, but the delay is because of these AND gates, right. So, if you keep adding more and more flip flops like this, if you go to Q4, Q5, Q6 and so on, what would happen is you would add one AND gate to each one of these. So, eventually what can happen is, for a wide enough width of the counter, you have several AND gates that you have to connect for the input to be, for the toggle line, right. So, at the nth stage of the flip flop, you will have n minus 1 AND gates, right. If this n minus 1 AND gates, if the delay of that is more than the clock width, then you will actually violate the setup time of the nth flip flop. So, that is what will happen, and the moment you violate the setup time, that flip flop can go into metastability. So, this is a concern, but this circuit is called a synchronous circuit. So, there are several ways in which you can cut down on the delay. You do not have to wait for n minus 1 AND gates delay, you can do better things than that, but as of now you can see that all the outputs are actually just clock to Q delay. Each of the bits are only a clock to Q delay away from the clock. They are not adding up, the delays from the clock are not adding up. There are a few variations that you can look at. So, this is a circuit which has both an enable and a clear. So, there is a enable line that is given as an input, and that is ANDed at each of the stages, and there is a clear bar line which is going into negative clear line. So, we will come to the clear part later. Let us look at the enable part. If enable is 1, then this T is 1, and earlier we had all this AND anyway, right. So, that will remain the same. However, if enable is 0, all the toggle inputs will be at 0, which means the counter will not count, right. So, this is not going to count. The clear signal, if clear bar is 0, then clear is 1, right. So, if clear bar is 0, then clear is 1, this will go and clear all the flip flops. However, if clear bar is 1, then this will be 0, which means the counter will count as though it is a regular counter. So, this is a fairly simple circuit which has enable added and clear added. You can also design these counters with D flip flops. In this case, you have a flip flop Q3, Q2, Q1, Q0. We have a single clock, so I do not know if you can see it clearly, but there is a clock signal here at the bottom that is going into the clock input of all of these. There is an enable line that is coming in, and there is a nice self repeating structure. So, Q0 is XORed with enable that goes as D input here, then Q1 is XORed with enable and Q0, and that is going as D input here, then Q2 is XORed with Q1 and Q0 and enable. So, if you go and look at this part of the circuit, it is enable and Q1 and Q0. If you have all three, that is XORed with Q2 itself, and that is going to be the input to this flip flop and so on. So, this enable circuit is as it was in the D flip flop, in the T flip flop structure. So, you go and convince yourself that putting an XOR gate will actually let you do this counting. So, in this case there is an up counter, you go and convince yourself that these are the values that Q0, Q2, Q1, Q2, Q3, what are they going to have when assume that all of them are initialized to 0, then go and see what would happen to each of these bits as and when every single clock comes in. So, if you want to keep it simple, go and look at Q0 initially, then add Q1 and look at how it is counting, then go and look at what Q2 is doing and see how it is counting, and you should see that it is working like a counter. You can take this circuit and you can also add a parallel load capability. So, what we have done to the previous circuit is, you see the AND gate structure and you see the XOR gate structure, they are remaining as they are, but there is a mux that is added before it goes to the D flip flop. And what is this mux taking? It is taking a select line which is called a load line. So, whenever load is 1, it is taking an external input. You can see that it is true for each one of them. So, there is D0, D1, D2, D3, all of them are taking external input, right? These are all external inputs, they are going to the mux. So, if load is 1, then the external input is placed as D inputs for all these flip flops, and that will become the starting value of the counter. If load is 0, this will work like a counter. So, what you are essentially having from this circuit is that if load is 1, you can load a value to the counter and then you make load equal to 0, and from there it will count. So, I can load a value 5 by making load equal to 1, and by putting 0 1 0 1 here, I can load a value 5 and it will start counting from 5 instead of counting from 0. So, it will start from 5, then go to 6, go to 7, go to 0, go back to 1, 2, 3 and so on. You can stop the counting at any point of time and load a new value. So, maybe I am going from 5 to 6 to 7 to 0, then I want to load 4. I can bring load signal by placing the value 0 1 0 0 here and bring a load signal. It will inhibit, it will prohibit counting up, however it will take the load value and count from 4 onwards. So, again I suggest that you go and look at how this works by drawing waveforms and convincing yourself that the circuit will work. Then you can do a few other things. So, this is a circuit which has a synchronous mod 6 counting. So, there is a clock signal and this has an enable signal, it has a load signal, and just like what we did in the previous one. So, let us take something like this. This will always count from 0 1 2 3 so on up to 15 and then go back to 0. So, I may not want to go to 2 power n minus 1 every time. So, if I use a 3 bit counter, it will go from 0 to 7 and then go to 0 and so on. What if I want a mod 6 counter? A mod 6 counter goes from 0 1 2 3 4 up to 5 and then goes back to 0, because a number modulo 6. So, 6 modulo 6 is 0, so it goes to 0, then from 0 again it goes 1 2 3 4 5 and again it goes back to 0 and so on. That is called a synchronous mod 6 counter. So, that is called a mod 6 counter, and this circuit is a synchronous mod 6 counter because we have taken the previous one, this circuit here, without the last stage, without the D3 stage. If we take the top part of the circuit and we do a small check, what we are doing is we are making enable equal to 1 always, and we are going to load 0 0 0, but the condition for load is that if I take 5, the moment I hit 5, the next clock cycle I want to go to 0, right. So 5 is 101, which means Q2 should be 1, Q1 should be 0 and Q0 should be 1. You take that condition, when Q2 is 1 and when Q0 is 1, you AND it together. This means this line will be 1 only when the counter has reached 5. The moment you have reached 5, then this AND will have a 1 that is coming in as a load for this counter. So the moment load comes in, from 5 it will not count to 6, it will load whatever is at the input. So D0 is 0, D1 is 1, D2 is 0, that will get loaded as the counter value. So Q0, Q1, Q2 will go to 0. So that is what you are seeing here. So it goes from 0, 1, 2, 3, 4 up to 5. When you hit 5, this AND gate will have 0. So till then it will be 0, you can verify that. So till you hit here, Q1 is this AND gate's output is 0, but at this point Q1 is 1 and it will load the current set of values. So there is also an asynchronous version of this which I have given in the slides. I suggest that you go and read through the asynchronous version and see how it works. So this brings me to the end of this sequential circuits. In the next module we will see basic sequential circuits which are slightly more complicated than the counters and other things that we have right now. So I will see you in the next module, and bye bye.